Okay, it's a pleasure to be here today, and I guess we've innovated in one respect. I've never seen a joint keynote before, so we'll see exactly how well this works. We've sort of imagined this as a dialogue, so we're not, Dr. Bush is from industry, I'm from academia. Obviously we have different perspectives on this problem of exactly how to foster innovation and the dialogue between academia and industry. And so I'm going to present you with some of my perspectives. So in my opinion, and I'm going to bolster this in my part of this talk, in my opinion, the value of the standardization process is twofold. Firstly, standardization has clout from industry, and secondly, standardization reduces risk for industry, and both of those mean it's much easier for academics to talk to industry through the standardization route than just by cold calling, for example. So it's a great way to bring the two sides together. So we've heard some possibly controversial remarks from Dr. Bush about academic research. Unfortunately, a lot of it was true. So I'm glad Steve talked about the incentive structure. So the fact is, academics are very intelligent people. And as very intelligent people, they naturally respond strongly to whatever incentive structure they're surrounded by. So what's the incentive structure in academia? Tenure and promotion are based on publications. Clout is based on publications. Funding is based on publications. So naturally, if you were to set this up as an optimization problem, your incentive would be to publish as much as possible with as little effort as possible. So this does not necessarily, as Steve noted, this does not necessarily lead to innovation. What it does lead to is a mountain of papers that possibly not everyone will read. And really the best case scenario or one of the best case scenarios for an academic researcher is to write a paper that 100 nerds will find impressive. So, this is not the complete picture of academia, however. Everything you've heard about academic research is also false. So, here are three highly innovative ideas. And what do these three have in common? This here is an MRI machine. So MRI works on the principle that if you apply a strong magnetic field to protons and then apply a resonant RF signal to them and then remove the RF signal, a signal will result which will allow you to map the density of water in tissues. This is a hard drive. Modern hard drives all include a technology called giant magnetoresistance, which basically manipulates the resistance in the read head based on the magnetic field below them. It is allowed, before giant magnetoresistance, it was thought that hard drives of this size would top out at about a gigabyte, and now we're up to a terabyte. This is graphene. This is the single layer of carbon atoms with the magical properties that will very soon revolutionize everything from electronics to sensors to solar cells to more or less anything you can imagine. So what do these three ideas have in common? Two things. Firstly, they all started out in academia. These all started out as visionary projects that originated entirely in academia before they were exploited by industry. What they also have in common is this: they were all winners of the Nobel Prize at some point. So my argument is, academia and industry need each other. There's no, why can't we all just get along? So there's no, there should not be a rivalry here. We should not be trying to suggest that one is better than the other because they're good at different things. So academia is excellent at the seeing farther, standing on shoulders of giants and visionary projects. So although the incentive structure in academia is set up to reward incremental change on research that is not necessarily innovative, tenured professorships, I see them as a platform to take risks. There's really nothing personally at risk in taking on a visionary and forward-looking project. So why not do it? So academia tends to be the best place we have for these visionary ideas. On the other hand, academia is really bad at knowledge translation. That is changing, but taking an idea bringing it into the marketplace, whether you think of that as the actual economic marketplace or the marketplace, the more philosophical marketplace of ideas, not so good at it. Industry is excellent at knowledge translation. So taking a concept that solves a problem and making money off it, that's what industry does all day. They're spectacularly good at it. What they're not so good at is looking 20 years into the future and trying to come up with visionary ideas that will blow open new fields of human endeavor. And the reason is because that doesn't increase shareholder value over the next quarter. So what I'm going to talk about a little bit today is some of my work and how this problem fits in with it. So this is one of those sort of visionary ideas. So imagine your bloodstream. And imagine that you could inject yourself with these guys, nanorobots, that swim through your bloodstream and do interesting things. What could they do? So these are we're just sort of blue skying ideas here. So what could they do? They could, for instance, if you have a disease such as cancer, they could swim through your body, find a tumor, inject chemotherapy drugs directly at the site of the tumor in concentrations that, if it was injected generally throughout your bloodstream, would kill you. So in other words, we could have chemotherapy treatments that are much more effective with far fewer side effects if we had this kind of a technology. Another idea, perhaps we could put it into invasive surgery. So imagine you tear your ligament. You tear a ligament in your knee, you go to the hospital, the doctor injects you with a vial full of these guys, they swim to your knee, reconstruct the ligament, and then eliminate themselves, and that's it. In an hour, you're basically back to normal. So the visionary possibilities for this kind of a project are enormous. And it might surprise you to know that this is closer than we might think. So, I mean, obviously this is an animation, and you might think of these devices themselves as science fiction. The fact is they're not. There are scientists and researchers, including some in Canada. There's a professor named Sylvain Martel at the University of Montreal who actually builds these devices. These devices exist, and they're here right now. We can also do things like program artificial organisms. Artificial bacteria can swim through your bloodstream and they can be programmed with arbitrarily created DNA, hopefully to do arbitrary things. So that's not the problem. These devices actually exist. What is the problem is that we don't know how to make them communicate with each other. One of these robots can't do very much, but again, like I said, if you can get them to all congregate somewhere and cooperate, that's really the problem that you need to solve. We call this field nano networks. This is not the only application. There are dozens of other possible applications of networking at the nanoscale, but this is the one that my research focuses on. So this is the one that I'm going to talk about. So the question related to this problem is, what can academia tell us about this problem? So again, academia gives us the vision. Academia sees further, stands on the shoulders of giants, and envisions what could be, and then hopefully takes research steps towards solving that. This is a project that has deep roots in academia. So the problem that I mentioned a second ago started being studied around the turn of the millennium, around 2000. That were the first papers trying to study exactly how communication can occur in different fields, such as a chemical medium. This is developed into the term molecular communication was first coined in about 2005 by a team of scientists at UC Irvine, and since then there's been a rapid expansion in research in this particular field. Now the problem, the problem is two things. We don't really have there's no visionary idea here. There hasn't yet been the equivalent of the E equals MC squared that blows open the whole field and is used as sort of a spotlight for other researchers. The other problem is this field is now taking off we don't really have an industrial anchor. There's not really any idea of how to take this knowledge and translate it to industry. In fact, we're right on the cusp of where we should be as far as taking these ideas into industry and perhaps exploiting them. So, if you'll indulge me for a few minutes, I'm actually going to talk a little bit about exactly how this problem is solved from an academic standpoint, just to give you a bit of a background. And the question that I'm going to ask is, if we're trying to solve the problem of nanoscale communication, perhaps we should look for solutions that already exist. So in fact, there exist nanoscale devices in nature. They look like this, and they communicate in a way that's completely foreign to the way in which communications engineers have traditionally tried to communicate. So most of the communication that we deal with in our research is electromagnetic in nature. So you can think of this as wireline communication, you can think of this as RF communication or optical, but fundamentally it's all electrical. If we're looking for inspiration from nature, we look to these kinds of nanoscale devices. Bacteria, how do they communicate? So it turns out what they do is they exchange molecules with each other. This is not surprising. It's been known for possibly even 100 years that this kind of communication happens. But until about 10 years ago, this was never studied by communications engineers. Communications engineers had far more, had a lot of things to do in wireless, but they never really touched this very much. So the question is, how do we take the vast body of research that exists about communications engineering and translate it to this new field so that engineers can actually design devices that can solve the nano communication problem? So if you're an information theorist like me, this will come as no surprise. More or less what we have to do is we have to take all of these components of the traditional communications model, selecting a message, transmitting it across the medium, receiving it in the presence of noise, and then trying to decide what kind of message was sent. Basically we need to take all of these components, which are still valid as an abstract model, translate them into molecular communication.